For the past year or so, I've had the honor and privilege to help out a few hundred startups using Datastax Enterprise, from getting started to know the technology all the way to production and even live issues in production. And it's been a really special opportunity for me. There's definitely been a lot of learnings that I've tried to encapsulate today in this talk. There's a couple of ways that I could have done this, but I decided to go pretty technical to try to capture just common issues that I saw, whether they're beginner issues or kind of more advanced tuning issues as well. And I just want to I went through just things that I saw quite frequently from startups asking for help. I want to thank all the startups that gave me the opportunity to help them out. And I mean, they're all doing really transformative things. They're changing the world in their own way with our technology. And so for Datastax, it's a great opportunity, and for me personally, to see those things in action and to try to help make them a reality. So, all right, the deck for this presentation is online. You can click the link at my Twitter handle right here. It's a little small, but if you guys can see it, just pull it up on your laptops. And there are some command line details, some technical stuff in there that will probably be useful later for any of you that are looking to deploy DSE in production. So it's an opportunity. You guys can look back at it. I want this to be a resource for later. Okay, so I want to talk about a little bit about the program high level very quickly. There's probably a way to make this full screen here. There we go. How you apply for the program and qualify, and a couple of statistics on the program for the last year. Then I'm going to talk about some getting started problems and how to solve them, how to get up and running with DSE, and common things that I saw folks fall over with in the beginning. And then I want to get into deeper tuning Cassandra and DSE problems. So what levers to pull when. Datastax and Cassandra are nothing if not tunable. And so there's a lot of levers, and you just have to know when to pull them and in what direction. And then finally, I want to close out with how can you best equip yourself for success for a deployment with Cassandra or Datastax Enterprise or both. So a little high level on the program. We offer basically our enterprise-grade software for free to any company that makes under 3 million in revenue per year or has under 30 million in funding, capital raised. And basically, there are no limits to the extent to which you use the product. You can use as many nodes as you want. You can use all the features. And yeah, I mean, that's about it. You get some perks. The perks include discount on our supports and services if you need them, discounts with some of our partners. They include marketing opportunities as well. There's a few folks in the room that I see here today that we've done some co-marketing with. And it's scenarios where both companies benefit when you guys are happy. And then also some free tech help, right? So that's new as of the last year. We used to just give folks the software and say good luck. And for the past 12 months-ish or so, I've provided technical help for all the startups around the world that are in the program. We've had, I think, over 600 startups sign up from more than 20 market verticals and more than 50 countries. So it's a pretty wide group of folks, again, all doing transformative things with our technology, and it's been a privilege to participate in that and to be a part of it. I'm going to dive right in. So one of the first things that I see a lot, so before I get into this, for support, the way that we handle it with a startup program, that is kind of really the only difference between a paying customer and a startup customer. A lot of our support is done via Stack Overflow for the startup program, and so yeah, if you're a startup, you post up there, and myself or a couple other technical folks from the company, we're always actually looking, the Ops Center team, other team members, helping out on Stack Overflow as well. And this is something that I see quite often up there. Hey, I started up Cassandra or I started up DSE and I can't connect, right? So I want to go through and some of this really the getting started stuff. What might the reason be, and how to troubleshoot when you can't connect to DSE? So some of the things to first check are, is the process up and running? A lot of the cases, the process didn't come up for one reason or another, And if that's the case, then you want to check your system log or output log to find out why it didn't come up. So these are scenarios, all these bullets are scenarios where a process didn't come up in a particular reason. So one reason may be there's another process running on a Cassandra port. So 7199, the JMX port, is being used by another process, so it couldn't come up. You'll see that in the logs. You may have an error, a problem with your YAML couldn't be parsed, so you'll see a snake error on in your system log. You may have a problem with your Cassandra environment shell. So for example, if you upgrade from one version to another and there's a different version of Jam that's packaged with Cassandra and DSE, you may have to just update your environment shell. And these are all things that you would see in your system log. You may have a bad upgrade. So sometimes if you're using Ubuntu and apt-get, you do an upgrade and some of the libraries didn't get overridden properly. And so I've seen some corrupted upgrades, and sometimes apt-get purge is the solution for that. There can be permissions issues when folks are using tarballs manually or using a .run installer. Sometimes the commit log directories and the data directories aren't available for the user that's running Cassandra, and so that will stop you from starting up. You may have old SS tables. I've seen this a couple of times during upgrade procedures with some customers. We were going through maybe a 50-node upgrade with one of our customers. The first 23 nodes restarted perfectly fine. The 24th one wouldn't come back up. We're scratching our heads trying to figure out what was different. Well, it turns out that that node had a couple SS tables that were super old. They were more than one version old, and Cassandra will actually not support SS tables that are too old. So what you want to do is make sure you upgrade SS tables from one version to another, and that way you don't run into this issue. But again, all this stuff you'll see in your system log, relatively clues to what the problem may be. When you're using DSE search, you may actually see a search load timeout, which is basically the amount of time for the search core to be loaded. This usually happens when your cluster is kind of under provisioned, and you have to play some catch up. But there's a configurable for you to increase how long you'll wait for the core to load when you're starting out. Also, something else. There are also replace node scenarios. So if the system tables aren't in the directory where they're expected, like if you are replacing a node, but that IP address is already being seen by the cluster, then you may have problems starting up as well, right? And so you actually have to run. There's a JMX flag that you can turn on to actually replace the existing node in the cluster, right? So that's something else. So these are all kind of examples, and you'll see based on your system log why your node isn't coming up. And yes, this is one of the most frequent things that you'll see on Stack Overflow is just folks trying to get up and started. There are a couple of scenarios where you can actually there's actually one scenario where your process won't start running and you won't see anything in your logs, right? And I actually see this more often than I would have expected. Your disk might be full, all right? And so obviously it can't write to the logs. So yeah, I've been on a couple calls and maybe I'm doing a screen share with somebody and I'll say, can you DF for me? And it turns out their disks are full. This happens a lot when folks upgrade, for example, from 2.0 to 2.1 because the commit log in Cassandra, which used to default to 1 gigabyte, is now 8 gigabytes in 2.1. And folks had maybe mounted it on their root partition, and that root partition was small. And so you're running out of disk after a little while and not able to come back up. And also you won't see anything in your logs, right? So that's a good one. Let's see. So there's a couple scenarios where DSE is up, but you can't connect, right? So let's talk a little bit about all the different addresses that you configure in Cassandra. One of them is the listen address. That's for node-to-node communication. So it's possible that the nodes can't talk to each other, and that's something you have to check in a network level. RPC addresses are for client communications to the nodes. And then you actually have broadcast addresses. There used to be just a regular broadcast address, that's the listen address. Now we also have a broadcast RPC address. So those are the addresses that Cassandra actually advertises to either nodes that are connecting or to clients that are connecting. So you have to check your firewall and your security groups to make sure that nodes and clients can actually talk to each other on those ports. Pro tip, Matt Kennedy did a ticket on Cassandra that actually created something called RPC interfaces and listen interfaces. So instead of actually specifying the IP in your YAML, you can specify an interface at the OS level, like ETH0. And so that way, you can actually configure all your nodes the same way without specifying and hard coding an IP, which can be nice for orchestration. So that's a good tip. Something else that can happen, if you're running security, your authorization key space might not be replicated. So that actually happens quite often, and folks get pretty confused. So just make sure if you're running security and the node's not connecting and talking and working out right, your auth key space might not be replicated. There's also, if you're using SSL, so encryption for node-to-node or client-to-node with Cassandra or with DSE, I've got a GitHub repo that actually helps set that up. This is clickable if you pull down the deck. All right, so something else, you can actually get some cryptic errors that are confusing if your OS level config is not set up properly. So these are some of the examples of things that you have to configure in order to get Cassandra to work correctly in Linux. But we do ship a pre-flight check inside of DSE that will check some of these things for you. So that's something else to take a look at if you're not using an AMI but kind of rolling your own boxes. Okay, so DSE has a lot of configurables. And I want to go through different scenarios, compaction, Tombstones, Bootstraps, and then search and analytics, and highlight some of the main levers for tunability. And so we're going to get a little bit more advanced than the last few pages that were just common issues. So compaction levers. The goal here, of course, is that you don't fall behind on your compactions so that you're able to continue to have fast reads. But you also want to minimize the impact that the background process that is compactions has on your reads and your writes. So one of the main levers that you can control is the number of concurrent compactors, right? So we used to ship by default that number to be equal to the number of cores in your box. And so sometimes if you're running that many compactors at the same time, you may actually have an impact on your reads and your writes. So I believe recently, at least in DSE, we're shipping that as a default to 2. So you're only going to see two compactions running at the same time. This is configurable, so if you're falling behind on compactions and you've got lots of CPU, something you can do is crank up the number of compactors. This is configurable at the YAML, but a lot of the time you're doing something, you're troubleshooting a live system, and you don't want to have to do a rolling restart, especially if you're running lots of nodes, to change a configurable like this. So you can actually change it via JMX, and you can do it programmatically with this JMX shell snippet. So you guys can pull the PowerPoint down and use the snippet to actually change your number of concurrent compactors on the fly in a box. And if you're using some orchestration tools like Knife, you can actually do that around your cluster as well pretty easily. All right, the second is compaction throughput, right? So we actually throttle compaction to 16 megabytes per second by default in Cassandra. And so yeah, if something that's happening, again, is you're falling behind on some of your compactions, you can increase that throttle, especially if you're running on SSDs. So a lot of folks that run SSDs basically just actually unthrottle this completely and leave it at 0. I seem to find that some throttling maximum is better than completely unthrottled. So I tend to set this to 100 or 150 megs per second in the scenarios where compactions are falling behind. So it's all about finding that medium where you're not falling behind on compaction, so you can still have your fast reads and not hit a lot of SS tables per read, but also not have that compaction process use too many of your system resources that read and writes get affected, and so your write throughput and latencies might actually get affected. Yeah. So the other piece about compactions is to make sure that you're using the right strategy. So I'll talk a little bit about size tiered, leveled, and day tiered, which are the 3 available compaction strategies today in Cassandra. So size tiered is the default. Basically what we do there is we will wait for a certain number of SS tables to reach the same size, and then we'll compact those together. And again, we'll wait for another set of SS tables to reach the same size, right? And so on and so forth. That's the default compaction strategy, and it's very good for write-based workloads. But there are no guarantees that at each level of sizes, your row will only appear one time, right? So you may actually have different instances of your row across the different levels, and so that's not necessarily optimal for situations where your read latencies are really crucial. So if you've got read latency SLAs that are very low, and you also have faster disks in the CPU, then you can use something called leveled, which guarantees you that you're only going to have one version of a row per level. And so that'll basically minimize, again, your SS tables per read. But the way that is accomplished is by paying a little bit more on your writes. Right? So as you're writing data and compacting, Cassandra's working a little harder to make sure that you only have one instance of a row per level. So you pay a little bit up front, but then your reads should be faster on the grand scheme of things. So fast disk is important for something like leveled. And then finally, day-tiered compaction. You guys saw Jonathan talk about it yesterday. We're seeing it as a potential solution for getting denser nodes in Cassandra, but it requires that, one, you actually know what the levers are to tune this, and two, that you have the right workload. Actually, it's probably the other way around. You need to make sure you have the right workload first. So one of the main things about day-tiered is that you need to have potentially a write-only workload, so that you're not doing any updates or deletes. You can have a TTL, and there are actually some benefits for running day-tiered and TTL. So basically, the point of day-tiered compaction is that Cassandra is aware that you're doing a time series workload that only does inserts and not updates and deletes, and so it's able to optimize the way that it compacts with that assumption. There's some levers, including a maximum number of time after we just stop compacting, and assume that there will be no more updates beyond that point. So today you have to be careful with things like read repairs and day-tiered compaction, because if you have, for example, read repair enabled, and you end up re-repairing data that's pretty old, well then you'll have tiny SS tables that are beyond the maximum compare date. Right? So things like that are gotchas in day-tiered, and you really have to watch out for those things. But there are a bunch of customers that are using it very successfully, both in and outside of the starter program, and are achieving denser nodes and also just overall lower CPU and disk utilization for compaction. So it's a very important, powerful tool if you have the right use case, and if you do your homework on the levers and on the gotchas, including like read repairs, things like that. Okay, so Tombstones. When we talk about Tombstones in Cassandra, we're not able to just delete data in Cassandra immediately when a delete comes in. Right? The reason for that is if there's a network partition, if there's a node that's down, and that node doesn't get the delete, when it comes back up, it would still have the old data. Right? So the way that Cassandra deals with that is by, there's a parameter called GC grace seconds, right, that Cassandra will wait as a minimum before it actually expires and garbage collects and deletes any tombstones, right? So we'll mark the data as deleted, but it won't actually get removed off disk until GC grace seconds has happened, and after a few more details are met, right? So if you need to get rid of some tombstones, right, because you actually have to go through those on your reads, and they may become expensive. You'll see, for example, on your logs, some tombstone warnings. Hey, we had to go through these many tombstones in order to accomplish this read. You'll see that in the logs. One way to clear that out is, well, first, make sure that your cluster is consistent by running a repair. But once that has happened, you can decrease GC grace seconds, and you can tune the compaction subproperties for tombstones that actually control whether or not tombstones in an SS table are compacted and deleted. So those levers are tombstone compaction interval and tombstone threshold. Tombstone compaction interval is a minimum number of days after which the tombstone becomes available for compaction, right? And the tombstone threshold is a percentage of data within the SS table that is composed of and comprised of tombstones. So there's actually a third lever called unchecked tombstone compaction that basically just ignores the other two and bases the ability to compact tombstones only and simply on simply on GC grace seconds. So yeah, so if you need to get rid of data and reclaim disk, this is the way to do it, and those are the levers. In order to actually do some introspection and find out if you have a tombstone problem and if your tombstone problem is resolved, you can use NoToolCFstats, which gives tombstone details, as well as SS table metadata, which is a utility that is shipped with Cassandra inside the tools folder, inside the tools directory. And you basically run SS table data and the SS table name, and you're able to see what tombstones are there and at what point they're actually expiring. Right? So you can actually see the number of tombstones that expired on April 1st or whatever. It gives you the epoch dates from 1970. So there's actually links out there to the docs and to other places. When you guys actually have this problem, you can come back to the slide. I think I might skip the slide, but there was a scenario that we, I'm not going to skip it. There's a scenario that we had, actually with somebody in the audience here, where the startup had lots and lots of tombstones, millions of tombstones, but only in a couple of rows. And this happened actually because tombstones also get generated not only when you do deletes, but also when you update collections. Right? And these guys were updating lots and lots of collections on a particular couple of rows. And so the nodes that own the primary key and the replicas for these rows were basically read, and they were having very long delays on both reads and writes. So what we did was first we identified what SS table had the problem, and we did that by using, this is a Brendan Gregg tool called OpenSnoop that actually allows you to check how frequently a file is being read in Linux. And that snippet will basically give you the most open files for the time period in your box. And this was actually used to identify what that SS table was that was getting hit so hard. Right? Once we had that culprit, that SS table, we looked at SS table metadata and confirmed that there were, in fact, a lot of tombstones limited to those rows. And then we actually used, and this Rudd Brasbury, I don't know if Russ is in this room, but this is his Python code that he used to look up using SS table to JSON and actually find out what were the rows that had all those tombstones, right? Because you can actually see them with a T in SS table to JSON. And then we tweeted about it, right? So if you click that link, you'll actually see a screenshot of DStat where you can see that the cluster before and after the two rows were deleted, and it was 90% utilization down to like 40% utilization. This is a beautiful thing, just by getting rid of the two. A very targeted surgical interaction that we did with Cassandra there. Okay, so Bootstraps. When you add a new node to Cassandra, you need to expand your cluster because, well, one, you need to start storing more data, or two, you need to write faster data, right? More writes per second, or reads per second. So this happens all the time in Cassandra, and sometimes folks, actually a lot of the time, I'll get calls or emails from folks that'll say, hey, my Bootstrap is stuck. It's hanging, and it's been hanging for a day, or for a week, or for however long, right? So there's actually a configurable in the Cassandra YAML called streaming socket timeout in milliseconds, right? And there's a JIRA here to set a default to that value, 8611. Actually, Rob Coley from the mailing list was the guy that fixed it, I believe. Yeah, if I recall correctly. But so up until now, there is no default for this value. And basically this value controls how long Cassandra will wait for a streaming job to complete before actually retrying. And it doesn't have a default, so Cassandra will actually wait indefinitely for a stream to complete. This works great if like networking is perfect within your data center, but that's not usually the case, and it's certainly not the case in the cloud where a lot of the startups that I work with are running, right? So there's lots of network gremlins, streaming sessions will fail, and then Cassandra will hang indefinitely. So before you do any bootstrapping, or actually go home and check your clusters and make sure that this has a value, right? Set it to an hour if you want to be very conservative. That's 3.6 million milliseconds, or set it to 10 minutes is probably more sane. But make sure that you have a value. Then there's streaming throttle, right? So you can actually, in the same way that we can set the compaction throughput, we can get and set the streaming throughput. And so that can actually accelerate or decelerate your bootstraps. And finally, once data is streamed from another node, you do have to compact it, right? And so the same levers that we talked about for compaction apply after your bootstrap. There is also a contingency strategy. So if you didn't have, for example, streaming socket timeout set, and you bootstrapped most of the way, we got 95% of the data, but then our streaming sessions hung, right? You don't have to start over. One thing you can do is clear your commit log, clear your data directory, bootstrap again. You don't have to start over. Just restart your node without a bootstrap false in the YAML and repair the rest of the way, right, if you almost made it. And so that can save you, depending on your data volume, a bunch of time. So we do this. We have to do this sometimes. What else do I have here? Okay, so something else that was introduced in 2.1 in these two JIRAs, so 2434 and 7069, is something called consistent range movements. So there's an edge case in Cassandra, in old school Cassandra, where under very pretty convoluted circumstances during a bootstrap, you might actually have one stale reads and even potentially data loss. So that got resolved in 2434. But then the stale reads are still a possibility. So after a bootstrap, because you're actually streaming data for somebody that owned the data before to the current node, if you do that to multiple nodes at the same time, you may actually not have the most consistent version of your data when you're reading. And so 7069 doesn't let you bootstrap two nodes at the same time that have part of the same ranges within them, right? To avoid this edge case. Now, a lot of the cases, you actually need to grow your cluster, and you're okay with potentially having a stale read, right? So if that's your scenario, you can actually add this JVM flag when you boot up, and it will allow you to bootstrap the two nodes at the same time. Yeah. So, okay, let's keep going. Okay, so those are the base Cassandra features that I wanted to go through, and I'll start talking about DSE search a little bit. So when it comes to DSE search and performance, we are interested in either indexing performance or query latency performance, right? So indexing performance is the amount of time that it takes and the throughput at which data goes from getting into Cassandra to also being available as part of the search indexes, right? And then query time performance is actually just the amount of time between your client and your response when you do a query. So those are the two main kind of things that you need to worry about when you're running search. DSE search actually co-locates Solr and Cassandra in the same JVM in the same machines, and so when data gets written into Cassandra, it automatically gets indexed into Solr, and that's the process how we get the data. So first, I want to talk about some monitoring for DSE search that you kind of want, things that you want to keep your eyes on, and then we'll talk about the levers that will help out to tune indexing performance and also query time performance. So monitoring DSE search, we have something called indexing pool stats. Here, actually, I want to click this. I've got a screenshot here. So this is what it will look like. Basically, we have JMX beans and beans for the thread pool stats, and we parallelize the number of threads that are used for taking the Cassandra data that's coming in and building indexes with it. Right. So in this case, there's a box that's running with 4 different thread queues. And you can see the process tasks at the top. You can see the queue depth, which is at 0, which is healthy. And you can see, I believe, the amount of time, the processing time in microseconds that it took the data to actually get in, to get in the index. So this JMX bean actually allows you to monitor real time as the data is coming in, how long it's taking through indexing, and how it's being spread out through the queues. You'll see in DSE 4.8 that we have an improvement here. So we used to split out the data that goes through each of those queues based on the Cassandra partition. And so if you had a super wide row within Cassandra, it would actually only heat up one of these queues. And you would see, for example, Q0 here with a very big number in cluster depth. But all the others were kind of relaxing, right? And so if you had wide rows in Cassandra hurt, but then they actually hurt more if you're using search as well. So yeah, so that's actually improved in 4.8. That's one of the big performance improvements that came through with that release. And then let's talk about commit and update stats. So these are actually gonna give you details on your timing. So there's different phases in the indexing process, and you can actually pull up the details of how much time was spent in each of those phases. So those are additional details that you can see for monitoring. So if I want to improve my indexing performance, something that I want to see So what are the levers that I have available? Right. So the first is something called soft auto-commit threshold, and that's the minimum amount of time that will go by before you actually start indexing data that's coming in through Cassandra. So I believe that by default we set this to 1 second in real-time indexing, but you can actually turn it down and get like faster indexing time. So this is the main lever. If you give DSE more time as a soft auto-commit, then it's easier on the resources. But if you actually need indexing time to be really fast, you need your data available for search right after you inserted it, then you can decrease this lever. And as long as you have enough CPU cores, indexing will actually work well. The second thing is number of cores per core. So that's kind of confusing. What does cores per core mean? That actually means the number of CPU cores that will be available to index a solar core. A solar core is like a solar shard. Right? So you want to set that to the number of CPUs available in your box. And so that's why we always talk about search indexing scaling with the number of cores available in your machine, right? And you can actually configure it here. There's something called back pressure that happens when we were looking at the queues before. If your queue depth reaches a certain level, then we're going to turn on something called back pressure. That's to avoid DSE search from actually OOMing. Right? So you can tune the back pressure threshold, right? The amount of queue depth at which it will start to slow down and actually load shed in extreme circumstances to avoid OOMs. And finally, there's something called a RAM buffer, which is it's part of the process. If you look at how Lucene indexes are built, there's something called a RAM buffer. The important thing about that is that you should set it to 2 gigs if you're using live indexing, and the RAM buffer itself is actually searchable with our new live indexing that dropped with 4.7. So those are the levers for indexing, and that scales with cores. And now we're going to talk about query performance. So the main thing about query performance is that you actually want to, search performance will perform very well if you can fit your Lucene indexes in page cache, right, in operating system page cache. So if you have enough RAM or your indexes are small enough, then you're going to have pretty good performance with DSE search. So there's a couple things that you can do to actually shrink your indexes. You can turn things off like term vectors and term positions and term offsets if you don't care about things like highlighting, which is a pretty nifty Solr feature, but you might not be using it. And things like omit norms, you can actually turn that on if you're not using something like boosts in Solr, right? So you can kind of disable some Solr features and shrink the size of your index if you don't have the hardware, the RAM to throw at it. And then you can also just index the fields that you intend to search on, right? So if you've got a table with 20 fields and you only really care about searching 5 of them, don't index the whole thing, right? All right. So what about the JVM? We talked about how both Cassandra and Solr are going to be running in the same JVM with DSE search. So what you want to do is actually increase the heap size for Cassandra. So if traditionally you're running an 8 gig heap with Cassandra, which is what we recommend historically, you actually want to run a larger 14 gig heap if you're running Solr. And if you're using the live indexing with DSE search that just dropped in 4.7, you actually want to have at least a 20 gig heap because it's going to put additional pressure on your heap because you're indexing so quickly. So the recommendation for live indexing is to run G1GC with 20 gig heap. And there's a couple of tricks to G1GC. Don't set a new gen size. I don't want to get into the rabbit hole of JVM tuning right now, but G1GC actually sets your new generation size dynamically, and so you don't want to hard code something there. And there's one lever in G1GC that's really important called max pause time in milliseconds, and you probably want to set it to 1 or 2 seconds, even though that sounds high, to get some pretty nice throughput with G1. All right, so there's also some common reason for OOMing with DSE search is if you're using collections really heavily and indexing those as dynamic fields. So be careful with collections and don't abuse them. If you want to know if you're abusing collections, just pull up Luke, which ships with DSE, and it'll actually, if it takes forever to load that page, you know that you're abusing collections. And as an alternative to using maps in dynamic fields with Solr, actually just use 2 tables and do a Solr side join, and that way that'll solve your kind of OOM bad news with dynamic field scenario. And there's a link there of an example of how to do that side join. Okay, so let's move into analytics. I think we're low on time, so I want to speed up. But with analytics, there's 3 really important things, right? Read Russ's blog posts, read Russ's blog post, and read Russ's blog post, right? So Russell Spitzer is one of our guys that actually built a lot of the Cassandra connector. This guy is excellent. At the end of this talk, in the slides, I'm linking to his blog posts. but most of the content from there has been either like directly out of his blog posts or things that he's helped me with when the startups are in trouble with particular analytics jobs. So read Russell's blog posts. And watch his videos too, he's really good. So a couple of levers just for getting started with Spark, right? A lot of the time something that'll happen is your Spark job won't run because you don't have enough resources available. It may not be that you don't have resources available in your hardware. It may just be that you haven't configured Spark to have the resources available. So Spark Executor Memory and Spark Cores Max are the main levers that you want there to make sure you have the resources available. Okay, then for reads, it's very easy. For reads and writes, it's very easy for Spark to overload, to overwhelm by doing lots of parallel queries like a Cassandra cluster, right? So what you do is you can actually control like the speed at which and like the size of the jobs and the batch sizes in order to control the speed at which you're reading from Cassandra and not overwhelm it. So the levers are input split size in megabytes and also the input page row size. There's also something else that's really important. In the same way that in Solar we co-locate search and Cassandra in the same boxes, with analytics we co-locate Spark and Cassandra. And so something that becomes important is data locality. You want your Spark executors to be reading the data from the disk on that same machine, right? And so there's a tunable called Spark locality wait, which is how long will Spark actually wait until a node, an executor on the local node where you need the data becomes available, right? Because it may be doing another job. So that's a tunable there. And if you want to actually take a look at exactly who it's looking for, what nodes are relevant for the partitions, this code snippet will give you the preferred locations, so the nodes that have the data that you care about for a particular RDD. All right, for writes, this is dense, isn't it? for writes, similar to reads, you don't want to overwhelm Cassandra, so there's a couple of tunables that you can use. So the number of concurrent writes and also the throughput megabytes per second that you can actually throttle Spark. And then, okay, so when you're actually building Spark jobs, we're going to get into just the performance of Spark itself and how it's written in your job. So what you want to do is make sure that for each Spark operation, you follow this sequence. So you want to make sure that you push most of the work down to Cassandra. So start out with Cassandra RDD specific work, right? And then move on to filters on the Spark side. Then do independent transforms, per partition combinable transfers, and finally full shuffle operations, right? So these are the examples of the actual methods in Spark that refer to the types of operations. But do wheres and selects before you do filters and samples, before you do maps by partitions, et cetera. And finally do joins and shuffles. And that's how you're going to kind of optimize your Cassandra, your Spark on Cassandra. So we talked about data locality. There's some methods in Spark that actually introduce a shuffle, which means ship all the data around your cluster, right? And if you're doing work on top of Cassandra, in the connector we have methods, alternative methods that will prevent you from doing that shuffle. So instead of doing a group by, use something called span by, and so you'll avoid shuffling the data around your cluster, and that will give you performance. There's a link there to the documentation that talks a little bit more in detail there. If you're looking at trying to do predicate pushdown with lots and lots of primary keys and partition keys, there's a method called join with Cassandra table that'll give you much better performance than actually like pulling up the whole table and then filtering it in Spark. So that's a useful method for writing lots of Spark jobs on Cassandra. And also, if you use collect and then do a bunch of work, realize that all that work is going to happen at your driver and not at your executor. So it's not going to be in parallel, it's going to be single-threaded. And actually, usually your drivers don't have a lot of resources allocated to them anyway. So don't do any work after a collect. Right, so those are some tips for building Spark jobs that'll give you performance boosts. A little looking forward, today DSE 4.8 dropped, and it ships with Spark 1.4. So these are the things that I'm really excited about. There's a lot of things that are there, but these are the things that I'm really excited about. I think we're out of time. There's meta monitoring capabilities. There's data frames that give you kind of the same interactions between Python and Scala and Java. And there's something called Job Server. And Ilya, who might be here, had a quote in an earlier talk this week that said, "I don't know how anybody uses Spark without Job Server, so check it out." I think that's it, actually. Oh, okay, no, I have a whole bunch of slides extra, but I think we're out of time. So, yeah, so here we go. And sorry guys, I know that this was a lot of information, but I wanted to get as much on paper accessible to people. That's my Twitter handle. It's Syllogistic. There's a link to the slides there. And there's a lot of meat there. I know that we're out of time, but if you guys want to ask me questions, I'm going to be outside for however long.